Okay, so today I'm going to go through the practice test. So this is one version of the practice test you see WebAssign, just with different numbers. And I'm just going to go through and work out all the problems and show you the steps that you need to take to work these problems on the real test. There are 7 problems altogether, and they'll all be given equal weight, although some are definitely easier than others, as you'll see. Now, you will be given 150 minutes in total, and you have 2 attempts, so an average 75 minutes per attempt, so 1 class period. Please keep in mind, once you start the test, the clock will not stop for any reason. If you start a test and you exit out, the clock keeps running. So do not open the real test, which will be posted on Monday, April 6th. Do not open it until you're actually ready to take it to devote the necessary block of time that you need. There cannot be interruptions or you will lose that time. Okay. Now, 75 minutes per attempt on average. If you use both of them, 7 problems, so you could spend at least 10 minutes per problem. But some are really quick and some not so quick, so please keep it in mind. The problems with undetermined coefficients, variation parameters will take longer. Budget extra time for those problems. Okay. For some reason this chalk's not erasing. Okay, first problem is reduction of order. So what you were given is this differential equation, x squared y double prime plus 2 prime minus 6y is equal to 0. And you're given one solution of this equation, y1 of x is equal to x squared. So x squared solves this equation. So your job in this problem is to find y2 of x. Now, this problem, the one in the real test, will be substantively different. It will be a reduction over problem. You'll be given a differential equation. You'll be given y1, and you find y2. That's all the same. But particulars like what y1 is will be different. But I'll show you the approach that you take regardless. So there's a formula given, and they actually give this in the problem. Formula for y2 of x. So it's equal to y1 of x times the integral of e to the minus integral of p of x dx over y1 squared dx. There's 2 integrals to work out. However, do not jump in too quickly because you have to make sure you have the right p of x. So the actual first thing you do, isolate y double prime. Divide by the coefficient of y double prime. So you have y double prime by itself. Then you have 2x over x squared, y prime minus 6 over x squared, y is equal to 0. And then you can simplify y double prime plus 2 over x, y prime minus 6 over x squared, y is equal to 0. The p of x is the coefficient of y prime after you divide. So it's this right here. So this is your p of x that gets substituted in here. So you must remember to divide by any coefficient of y double prime before you identify your p, or everything will go wrong. Sorry, a little interruption there. Okay, so now we can fill in our p of x and also our y1, which is x squared, and work out this whole expression. Okay. So y2 of x is equal to x squared, that's y1, times the integral of e to the minus integral of 2 over x dx all over y1 squared. Well, y1 is x squared, so what goes down below is x squared squared. Okay. Now, so we're looking at the integral, we have e to the minus, integral 2 over x is 2 natural log of x. And all this is over y1 squared, so that is x to the 4th. Sorry. Now we can use one of the properties of natural logs. So we can take this, whatever's multiplying the natural log, we can move up here as the exponent of whatever it is we're taking the log of. So we're going to have e to the natural log of x to the minus. All of this is over x to the 4th. Okay. Now we can cancel out the e and the log, and what you have is x to the minus 2 over x to the 4th. So we subtract the exponents, we get minus 2 minus 4. So what we really have is x to the minus 6. So I fill that in down here. So we still have the x squared sitting outside. And then we have x to the minus 6 dx. So now we go ahead and work out this outer integral. That gives us x squared x to the minus 5 over minus 5. Don't bother with a plus c because that would be redundant. Just be adding on a multiple of y1 solution. Now we simplify this and we get x to the minus 3 over minus 5. Now, for the final answer, you can drop any constant factors because when you have this equation like this one, any multiple of a solution is also a solution. So we will say that y2 of x is equal to 1 over x cubed, or x to the minus 3. So this is the final answer here. So, so first divide by any coefficient of y double prime. You must do that up front. Then the coefficient of y prime is your p of x. Use this formula, which will be given to you on the test. And then you have this integral and the outer integral to work out. Any constant factors, you do not need to include them in your answer. So here's a second solution. Y2 of x is 1 over x cubed. So that's reduction of order. Now, the next few problems are actually fairly quick. So I want to go through real quickly, claim those points so that you can spend more time on the other problems that are more involved. So, number 2. And from problems 2, 3, and 4, you actually to find the general solution. So there will be some arbitrary constants here. 6y double prime plus y prime is equal to 0. So, so an equation like this where you have 0 on the right-hand side, so it's a homogeneous equation. First thing you do, you get the characteristic equation. So order of differentiation goes to powers of your solution r, so 6r squared plus r is equal to 0. Okay, so now to solve this characteristic equation, we can go ahead and factor. What's a common factor? It's r. So factor out an r, and what's left is 6r plus 1 is equal to 0. So now you can set both of these factors equal to 0 to find the values of r that solve the characteristic equation. So what we get is, well, from the first one, r is equal to 0, and then we have 6r plus 1 equals 0, so we have 6r equals minus 1, therefore r is equal to minus 1, 6. Okay. So now that we have the two roots of a characteristic equation, we see that they are distinct real roots, so the general solution will consist of exponentials. So y of x is equal to c1 e to the 0 times x plus c2 e to the minus 1/6 x. But e to the 0 is 1. So we have c1 plus c2 e to the minus x over 6. So that is your final answer. These are my notes. I have the terms in opposite order. So I have I have c1 e to the minus x over 6 plus c2. WebAssign doesn't care what order the terms are entered in or which has a c1, which has a c2, because it's certainly the same general solution. So there you have it. So you can just find your two roots. When they're real distinct, then you have exponentials with those roots as the coefficients of x, and they're multiplied by arbitrary constants and added together, and that's it. Problem 3, very similar. You're also asked to find the general solution. So I have y double prime plus 4y prime plus 4y is equal to 0. So your characteristic equation, so we have y double prime gives you r squared, 4y prime gives you 4r, and then 4y gives you just 4. That is equal to 0. So this can be factored nicely. Also, if you can't see how to factor it, you can always use the quadratic formula. You get r plus 2 is equal to 0. So there's only one root that's a double root. R is equal to minus 2. So when you have a repeated root, don't forget, there's a common mistake. You are going to have exponentials, but one of the exponentials has to be multiplied by x. So you have to have two distinct solutions, y1 and y2, that get multiplied by constants. So the general solution will be y of x is equal to constant e to the minus 2x plus another constant. Don't forget the x when it's a repeated root, and then you have e to the minus 2x. So that is your final answer in this case. So, and yeah, on the test, you're gonna have a real test. You're gonna have the three different scenarios come up: two distinct real roots, a repeated root, and then the next problem, problem 4, I'm going to do now, will have complex roots. All right, so this fourth problem will also be a relative quickie. Again, asked to find a general solution of y double prime minus 6y prime plus 10 is equal to 0. So once again, you find the characteristic equation. So r squared minus 6r plus 10 is equal to 0. So this is one that does not factor nicely. So we go ahead and use the quadratic formula. So r is equal to minus b, so that's 6, and plus or minus square root of minus 6 squared, so 36, minus 4 times a times c, so times 1 times 10. So 36 minus 40 all over 2. So this is what the quadratic formula gives you. So more specifically, it's minus 6 squared minus 4 times 1 times 10, just to make sure you see where this comes from. So now we can start simplifying. So we have 3 plus or minus square root of minus 4. Well, square root of minus 4 is 2i. So we have 3 plus or minus 2i over 2. So we get 3i. So those are the complex roots of the characteristic equation. So now we can jump directly to writing down a general solution. The real part is 3. That goes in your exponentials. The imaginary part is 1. So that goes into the sine and cosine. So we have y of x is equal to a constant, e to the 3x cosine x plus c2 e to the 3x sine x. So this is your final answer, the general solution. So the minus b over 2a part, that goes into the exponentials. What do you get? That's multiplying the I. That goes into the sine and cosine as the coefficient of x. All right, so distinct real roots, you have exponentials. Repeated roots, you have an exponential and x times an exponential. Complex roots, you have e to the real part times x times cosine and sine of imaginary part times x. Okay. So for the quicker problems, the not so good, unfortunately. So the next two are non-homogeneous equations, where you have to use either the method of undetermined coefficients or variation of parameters. Okay, so problem 5, we have y double prime plus y prime is equal to minus 4x. And this is an initial value problem, unlike the previous ones. So you're given that y of 0 is 0, 0 is equal to minus 15. Now, first thing you do is what you were doing in the previous 3 problems. General solution of the homogeneous equation. So we temporarily set aside the right-hand side. So we have 5y double prime plus y prime is equal to 0. So you're going to proceed as in the previous 3 problems and write down a general solution of this. So we have a characteristic equation like before, 5r squared plus r is equal to 0. So you can factor out an r squared there, times 5r plus 1 is equal to 0. So now, similar to this problem 2, the roots, we set our factors equal to 0. So r equals 0, and 5r plus 1 equals 0, so 5r equals minus 1. So r is equal to minus 1/5. So now I'll write down the general solution of a homogeneous problem. So I'm going to refer to that as y sub h of x, h for homogeneous, is a constant times e to the minus x over 5 plus c2 c2 e to the 0 times x. So it's c1 and c2 times e to the root x, because we have 2 distinct real roots. So let's simplify. So you get c1 e to the minus x over 5 plus c2. So distinct real roots, exponentials. All right. Now, that's for a homogeneous problem. Is find a particular, and for this problem, I'm going to use methods. All right. Now, what you do is you look at the right-hand side. The right-hand side, in this case, is a polynomial of degree 1. So we have x to the s times a1x plus a. So here's our polynomial degree 1 that's part of our particular solution, where the coefficients a0 and a1 are undetermined. That's the method of undetermined coefficients. Times x to the s, where s is times 0 is a root of the characteristic equation from the homogeneous homogeneous problem. Now, so what happens here is, since we have a polynomial here, there's no exponential, there's no sine or cosine, we need to see, is 0 among the roots of the homogeneous equation? So we look, and yes, it is one of the roots. Therefore, the number s is equal to 1. So you have to take that overlap. So we're going to have x times a1x plus a0. And now we go ahead and distribute. So we have a1x squared plus a0x. So this is the form of your particular solution. So it's a polynomial. It is a polynomial of minus 4x. And we have to multiply by x because 0 is one of the roots. So don't forget to check for that. So what we need to do next is substitute our particular solution, yp, into the original differential equation. And for that we need the first and second derivatives. So yp prime is equal to the derivative of this. So that's going to be 2a1x plus a0. And we also need the second derivative. Yp double prime is going to be 2a1. So now we have the particular solution, its first and second derivatives. So now we can substitute all of these into here, into the original differential equation. So we have 5 times the second derivative, which is 2a1, plus the first derivative, 2a1x plus a0. And that is equal to, to match it right side, the minus 4x. Okay. Now, let's multiply everything through. So we have, on the left side, we have 10a1. And then I'm going to take any other constant terms and include it. So a0. Group by like powers of x. So we have these two constant terms, I'm grouping them together. And then I have this one linear term here, so plus 2a1x. And that's equal minus 4x. So now what you can do is match up like powers of x on both sides of the equation. So for instance, for a linear term, we have 2a1x and minus 4x. So we have 2a1 is equal to minus 4. And then there's no constant term over here. So this constant term has to disappear also. It must be 0. So we have 10a1 plus a0 is equal to 0. So these two equations you must solve, a0 and a1. Now the first equation we can easily solve for a1. So a1 is equal to minus 4 over 2, so that's minus 2. And then we can substitute that into here. So we have minus 20 plus a0 is equal to 0. So that gives you a0, 20. So now we have the coefficients of a particular solution have now been determined. So now we can write down our particular solution and combine that with our homogeneous solution to have our general solution. So I'm going to fill in these constants for in here for A1 and A0. So I need to erase to complete this problem. Well, I just realized I should have left some things there. Okay. Put back the rest of the original problem. Okay. So here's the original problem. And here's a particular solution with the values of A1 and A0 that we can fill in. So yp of x is equal to A1, so it's minus 2, x squared plus A0, which is 20, times x. So that's our particular solution. Therefore, the general solution is y of x, which is equal to the homogeneous solution, which I wrote down earlier and then erased, the particular solution. So the homogeneous solution is C1 e to the minus x over 5 plus C2. That's a homogeneous solution. And then I fill in this particular solution. So minus 2 plus 20x. So what's left is we need to use the initial conditions to get the values of C1 and C2. So so by applying the initial conditions, I need y prime. So because we need y of 0 and y prime of 0. So y prime of x is equal to minus 1/5 C1 e to the minus x over 5. Derivative of C2 will be 0. And then we have minus 4x plus 20. Okay. So now that I have y of x and y prime of x, I can y of 0 and y prime of 0. So if I fill in x equals 0 over here, we're just going to get C1 plus C2. And that has to be 0 because 0 equals 0. Y prime of 0, I plug in x equals 0 here, and I get minus 1/5 C1. That part is 0, and I get plus 20. And that is equal to minus 15. So now I have these two equations, linear equations, that I can solve for C1 and C2. So from the second equation, I can use the second equation to solve for C1. And then once I do that, I'll know that C2 is just equal to minus that. So I have minus 1/5 C1 is equal to, I'll move a 20 to the other side, and I get, so now I can multiply both sides by minus 5. So I get C1 is equal to minus 35 times minus 5, which is equal to plus 175. And now I can take that value and substitute it into the other equation and get the value of C2. So that is minus 175. So now I can finally, so if I substitute these two values into here, which is my general solution, I have my final answer. So I'm going to have 175 e to the minus x over 5, that's C2, minus 2x squared plus 20x. So this is the final answer with the initial conditions taken into account. Okay, so now 2 problems to go. This next one, unfortunately, another somewhat lengthy one because that deals with it also deals with a non-homogeneous equation. There's a variation of parameters for this one. Alright, so for problem number, I need a better piece of chalk. 6. Oh, not that piece of chalk. Okay. So I have 3y double prime minus 6y prime plus 6y is equal to e to the x secant of x. Now, one thing you can tell right off the bat, because of the right-hand side, we cannot use coefficients for this one. And the reason is the form of a right-hand side for undetermined coefficients is going to be, has to be either a polynomial or an exponential times polynomial or a sine or cosine times a polynomial. And this does not fit either one of those forms. For that reason alone, even though the left-hand side of the differential equation has constant coefficients, there's still variation of parameters. Okay, so like before, we must come up with the general solution of a homogeneous equation. Now this problem, number 5, no initial conditions are given. We just write down a general solution. So a homogeneous equation is 3y double prime minus 6y prime plus 6y is equal to 0. So now we need to get a characteristic equation. All right, so this is our first step here. So characteristic equation is going to be 3r squared minus 6 is equal to 0. I'm going to divide through by 3. This is a common factor. So r squared minus 2r plus 2 is equal to 0. Now this actually does not factor nicely. We can use a quadratic formula. So r is equal to minus b, so plus 2, plus or minus square root of minus 2 squared minus 4 times 1 times 2 all over 2. So we're going to have 1 plus or minus square root of 4 minus 4 times 2, so 4 minus 8. So square root of minus 4 over 2. Well, square root of minus 4 is 2i, 1 plus or minus I. So those are the roots of the characteristic equation. They are complex, therefore we're going to have exponentials in sine and cosine. So our homogeneous constant C1 e to the x cosine x plus constant C2 e to the x sine x. So the e to the x comes from the fact that the real part is 1. The imaginary part is plus or minus 1. So that leads to cosine of x, sine x. Remember, the real part is a coefficient of x in the exponential. So it is purely imaginary, you don't have an exponential. The imaginary part is a coefficient of x in the sine and cosine. So that's why we get cosine x and sine x. So now we have our homogeneous solution, and our two solutions, e to the x cosine x and e to the x sine x, the things are multiplying by constants. Those are y1 and y2 that we're going to need for a variation of parameters. Okay, so now the second thing that I'm going to do is what's left is a particular solution. The first step in getting a particular solution is a Wronskian. So Wronskian, capital W of y1 and y2. So a general formula for the Wronskian is y1, y2 prime minus y2, y1 prime. So we need y1 and y2 and their derivatives. So I have e to the x cosine x times the derivative of e to the x sine x. So I'll just fill in a prime here. Minus e to the x sine x, e to the x cosine x prime. Okay, now we need the derivatives. Because of e to the x sine x or e to the x cosine x, you need a product rule. So that'll give me e to the x cosine x from before, and I'll have sine x times the derivative of e to the x, but that's just e to the x, plus e to the x times the derivative of sine, which is the cosine. Minus with e to the x sine x from before, and same idea, product rule. So we have e to the x cosine x plus e to the x times the derivative of cosine, which is minus sine. So that's going to put a minus here. So now we need to simplify all this. Quite a mess to clean up. So I have, when you're multiplying e to the x's, you add the exponents, so we're going to get, every term's going to have an e to the 2x. So I have e to the 2x cosine times sine, plus e to the 2x cosine times cosine, so that's cosine squared. And I have minus e to the x and e to the x, that's e to the 2x sine x cosine x. Minus and minus makes a plus. So I have e to the 2x sine squared. Okay. Now what happens is first and the third terms, identical except for the sine, they will cancel. So now what's left is e to the 2x cosine squared plus e to the 2x sine squared. This will simplify quite a bit. I'm going to factor an e to the 2x out of both. So I have cosine squared x plus sine squared x. The only trig identity that students tend to remember, cosine squared plus sine squared is 1. So the Wronskian is just e to the 2x. And actually this happens in general when you have complex roots like this. The Wronskian will always turn out to be e to the 2, e to the 2 times the real part. Which in this case, the real part was 1. So for example, if I had e to the 3x cosine 2x and e to the 3x sine y1 and y2, the Wronskian would turn out to be e to the 6x. Just going through this process. Okay, so now we have a Wronskian e to the 2x, and we will need that in our formulas for variation of parameters. So erase this. We'll erase everything. A certain thing, homogeneous solution. Oh, never mind. I erased it. That's okay. I have it in my notes. Okay. All right. particular solution, so our next step is the formula for a particular solution is yp of x is equal to w1y1 plus w2 y2, where w1 and w2 are unknown, so we'll have formulas to get them. So y1 is e to the x cosine x in this case, and then y2 is e to the x sine x. So our formulas for w1 and w2. So w1 is minus the integral of, so if we refer to the right-hand side as g of x. Okay, now, one thing that's very important, we do have formulas for the unknowns w1 and w2. Let me write those down first, just the general formulas. So w1 of x is equal to minus integral of y2 times g of x, which is the right-hand side, over Wronskian. And then w2 of x, no minus integral of y1 times the right-hand side g of x over the Wronskian. Now, very important, before proceeding to use these formulas, you must have a right g of x. This is not the right g of x. You must divide by any coefficient of y double prime. So I need to divide by 3 in this case. So I will divide by 3. So I have y double prime by itself. Divide these coefficients by 3. So these coefficients become 2. And then I have a 1/3 e to the x secant x. So do not forget to do that. Now, I probably should have done it at the very beginning of a problem. It's a good idea just to get that over with right away. It wasn't really necessary back then, but it's for a general solution, but it's certainly necessary now. So now I can go ahead and fill in all the pieces. So for w1, I have minus integral of y2, which is e to the x sine x, times g of x, which is 1/3 e to the x secant x, all over the Wronskian, which was obtained earlier. That's e to the x. Now we simplify a lot. That always happens in these problems. I have e to the x twice up top, so multiplied together, that's e to the 2x. But it cancels with the e to the 2x down below. So all the exponentials cancel. And what's left, I have minus integral of sine x, and secant x is 1 over cosine. So I'm going to put the cosine in the denominator. Okay. Sine over cosine, that's actually tangent, but you can also work out the integral this way by leaving it as sine and cosine. I let u equal to cosine. So du is minus sine x dx. So that's convenient because there's minus sine x dx as a whole new. We have the integral of 1 over u du, which is natural log of absolute value of u. Don't forget the absolute value in the log for web assigned. So we get, sorry, my apologies. I had the 1/3 here, and I dropped it at this step. So minus 1/3, and then I still have 1/3. The minus went away because it's part of the du, but the 1/3 is still there. Apologize. Let me fix all this. 1/3 natural log of absolute value of u. And now we undo the substitution. So we get 1/3 natural log of absolute value of cosine x. So that is the w1 that goes into the particular solution. Now we work out w2. So again, fill in all the pieces. y1 is e to the x cosine x. G is e to the x secant x over Wronskian, which is e to the 2x. Same thing happens as before for cancellation. We have e to the x up twice, so that's e to the 2x, canceling with the e to the 2x down below, so all the exponentials go away. We'll plot to 1/3. And then cosine x is 1 over, well, sorry, secant x is 1 over cosine, or I could have said cosine is 1 over secant. The point is, cosine and secant are reciprocals of one another, so you multiply them together and you get 1. So what you get is just 1/3 x. There's no need for a plus c with these because that would actually be redundant. So now we have the W1 and W2. So finally, I can write down the particular solution by taking W1 and filling them in here. So a particular solution is W1, which is 1/3 natural log of cosine times y1 cosine x plus W2, which is just 1/3 x, times y2, which is e to the x sine x. So now I can write down the general solution, which is just the particular solution plus the homogeneous here. We have no initial conditions to deal with, so y of x is going to be constant c1 times e to the x cosine x, so c1 times y1 plus c2 times y2, which is e to the x sine x, plus the particular solution. So 1/3 natural log cosine e to the x cosine plus 1/3 x e to the x sine x. So this that I've boxed here, that is your final answer, the general solution. So find this homogeneous solution first to get your y1 and y2. Take the Wronskian of them, so y1, y2 prime minus y2, y1 prime, that turned out to be e to the 2x. Use these formulas to find the unknown portions of W1 and W2 that fit the form of your particular solution. Once you have a particular solution, just add it to the homogeneous solution, and then you're done. All right, so now there's just one problem left. This is a spring mass system, like I was covering on Monday. So, presumably this problem shouldn't take quite as long, I hope. Okay, so what we have is a force of 960 newtons stretches a spring 4 meters. So L, the length, capital L refers to the length that the spring is stretched by the object or whatever force that's imposed on it is 4 meters in this case. The mass of the object attached to the spring is 60 kilograms. So what happens is it's at its equilibrium position, so it is not pushed or pulled in any way. So I could use x of t, the object on the spring. So x of 0 will be 0 because it's at equilibrium. Okay. And is given an upward velocity is of 6 meters per second. So that gives the other initial condition, x prime of 0 is equal to minus 6. Remember, downward is positive, upward is negative in our coordinate system here. So we have our two initial conditions, and there's no mention of damping. So since it's not mentioned, we just assume there's no damping. So the problem is to find the equation of motion, which is x of t. So x of t has these initial conditions, and equation of motion, we need to solve this differential equation. So it's mx double prime plus kx is equal to 0. So not only is there no damping, but there's no mention of any external force either. So we just have this equation right here. Now we're given m, the mass, that's 60. So we have 60 x double prime. K, I do not have a spring constant k. So to obtain that, we use the fact that whatever force is imposed via spring is equal to the spring constant that we're after times the length. Now, in previous examples, I've used the forces to be the force due to gravity, so mg. But in this case, we're given an amount of force and how much that stretches the spring, so we're going to use that. So F is 960, is equal to K times 4. So we just solve for K. K is equal to 240. So that's what goes here. 240x is equal to 0. So this is a differential equation we need to solve. And then once we get a general solution, we'll make sure it satisfies these initial conditions. Let's divide both sides by 60 for convenience. So I have x double prime plus 4x is equal to, okay. Now, so what happens in this case, the characteristic equation, we have r squared plus 4 is equal to 0. So r is equal to plus or minus 2i. We have complex roots, so the general solution is x of t is equal to a cosine 2t plus b sine 2t. Now, another way to arrive at this point for these spring problems, the coefficient of t in the sine and cosine is the natural frequency omega naught, which is always the square root of k over m. And we had those values earlier, so k is 240 and m is 60. So you can always get the coefficient that will happen if you just use a characteristic equation. So whatever approach you take, this is going to be the solution in this case. So we have our general solution. All that's left is to satisfy the initial conditions. So I need x prime, the initial conditions is on x prime of 0. So I'm going to get minus 2a sine 2t plus 2b cosine 2t. So now I can substitute t equals 0 into both. So I have x of 0. Well, cosine of 0 is 1, sine of 0 is 0. So I get a times 1 plus b times 0. I just get a. And that has to be 0, because x of 0 equals 0. So that term is gone. So an x prime of t is equal to 2b, and that has to equal minus 6. So b has to equal minus 3. This coefficient of minus 3 gets filled in here, and so now I can write down the final answer. X of t is equal to minus 3 sine of 2t. All right, so that completes the practice test. This is posted on the course website, also in the lectures page under the entry. So I would encourage you to work through one of the practice tests. I have one that is not timed and 5 versions that are timed. and you can see in most problems, but you get an idea of how the solutions will play out, so that when it's time for you can hopefully get all the right answers. So there you have it. And if anyone has any questions about the test, between now and Monday, I will record a video for Monday afternoon in which I will address those questions. Otherwise, there just won't be a video, which I'll announce. And Monday is also when I will make the test available on WebAssign for you to start. So good luck.